Okay, sir. It's my pleasure to introduce today resource person Dr. S. Kannimuthu, Professor, Department of IT, Karpagam College of Engineering, Coimbatore. He has completed his UG degree BTech IT in the year of 2005 at Park College of Engineering Technology, Coimbatore. He has completed his PG degree ME in the year 2007 at Kongu Engineering College, Erode. Completed his PhD in Anna University 2015. He has 14 years of teaching experience and his area of the interest are machine learning, big data analytics, artificial intelligence, data structures and algorithm design. He is a data science consultant for MacByte Technology Coimbatore. He is a mentor for the Divine Info Tech Private Limited Coimbatore. He is an expert member for Student Learning Assessment Project Cell AICT. Received Favorite Teacher Award for Karpagam Institution and received Academic Excellence Award at Park College of Engineering and Technology. Received Faculty Endowment Award from the Management of CIET for successfully completed for PhD work. Completed 601 online certification courses in Coursera. Completed 41 specialization courses and 4 professional certificates. He has also received 24 badges for LinkedIn skill assessment courses. Completed 5 NPTEL courses with elite grade and published 4 patents as Anna University Supervisor Guide is 7 research scholar and produced 2 research scholar. He has delivered 129 grade lecture in recent technologies. He has patent in 18 papers in national and international conferences. He has also acting as a BOIS member for Sri Krishna College of Engineering and Sri Saraswati Tyagarajar College and acting as a DC member for 22 research scholar. Published 5 books chapters and 55 international journal papers and 9 conference papers. Acting as a reviewer in 43 journals, he is always a lifetime member in ISTE, IAENG. With this, once again, I welcome the all participants for this wonderful session by such a great personality. Thank you once again.
Thank you, ma'am.
Thank you, sir.
Thank you so much, sir.
I think you may able to view the screen. Are you able to view the screen, ma'am?
Yes, sir.
Yes, sir.
Yes, sir. Visible, sir.
Yes. Thank you, ma'am. Thank you, sir. Good evening, all.
Yes, sir, it is visible.
Good evening, all. This is Dr. S. Kannimuthu, Professor, Computer Science Department, Karpagam College of Engineering. Today, I wish to present my first session titled Quantum Gates. I wish to discuss about foundations, advancement in quantum computing and applications. Before getting into the session, I must thank the management of Dhanlaxmi Srinivas Engineering College, AICT Training and Learning Academy, Principal Sir and Head of Department of IT and CSE, and Professor Gobi and the coordinators for providing this wonderful opportunity to present the session. The overview of my session is mentioned here. I wish to introduce about quantum computing. Then I come across foundations of quantum mechanics. Then I move on to quantum gates, introduction to quantum gates, and the composite and universal gates. Then I will discuss about physical realization of quantum gates. Then I will come across recent developments in quantum gates and applications. Finally, I conclude this first session with research challenges and opportunities, which is pertaining to quantum computing. First, I start the session with the introduction of quantum computing. Actually, quantum computing is a new computational paradigm or computational style that makes use of the principles of quantum mechanics, such as superposition, entanglement, and interference. These are all used to perform calculation that are infeasible for classical or digital computers. There are several key features we realize with respect to quantum computing. First one is qubit representation. In digital computers, we use classical bits, zeros or ones. Actually, qubits exist in a superposition, that is in the intermediate state between the 0 and 1, which represents a combination of 0 and 1 simultaneously. And also, another feature is parallelism. We can exploit or make use of quantum parallelism, which can able to perform several computations at once. Then, entanglement is another feature, significant feature which is available in quantum computing, which enables strong association between the qubits, which permits enhanced computation and communication capabilities. And also, we achieve speed, that is high speed computations. Speed up enable to exponential speed up in specific algorithms such as Shor's algorithm for factorization and Grover's algorithm for searching. So we realize high speed response for solving the problem such as factorization as well as searching process. And what is the significance of quantum computing technology and research? Now, we have significant transformation in problem solving, such as quantum computing enables breakthroughs in fields which requires high computational power, such as cryptography, drug discovery, and optimization. And also it create economic impact. We have predicted to significantly influence sectors like finance, logistics, and AI. And also, quantum computing permits us to solve fundamental problems in physics, chemistry, and material science. Here, I'm in a position to compare quantum computing with the digital computers in terms of several aspects. In classical computer, the basic units is represented or mentioned as bit, which is either 0 or 1. But in quantum computing, we realize 0, 1 as well as superposition state. In classical computer, digital computer, the state represented as binary, it is fixed state 1. And in quantum computing, we have quantum superposition state. In digital computer, the data processing in terms of sequential or parallel. We have there are several researchers going on developing the sequential algorithm as well as parallel algorithm. The algorithm which is used for sequential may not be applicable for parallel algorithms. The algorithm design also different. But in quantum computing, we realize massive quantum parallelism with the help of high computational power. And in terms of error tolerance, we have well-established error correction. But in quantum computing, we are in need of advanced quantum error correction, which is under research. In digital computer, the algorithms are deterministic one, but in quantum computation, the algorithms are probabilistic one. Which is relevant, which is related to probability theory. The state of a qubit, which is relevant or specific to the probabilistic state. So the algorithms are developed by using quantum computation, relying on the probabilistic methods. So we have one extra state called superposition state, which is the state in between zero state and one state. And also we have another feature called interference, which is used to associate, one state to another state. We have realized several intermediate state with the help of interference. And also the qubit states are associated or communicated with the help of quantum entanglement. The key advantages of using quantum computing includes we have achieved quick response for solving several state-of-the-art problems. One is SARS algorithm, which exponentially outperforms classical factorization, and another one is Gruber's algorithm, which provides a quadratic speedup for unstructured research, which is not feasible in sequential algorithm or classical digital computing. And also we can perform complex simulation by using quantum computing. Quantum computing is responsible for simulating molecular structures and quantum systems where digital computers fail to do due to high computational power. And in digital computer, we face several issues, which is also applicable for quantum computing. Quantum computing is not a replacement for digital computing, but it is a complementary technology for specific tasks. Current quantum hardware faces issues like decoherence, noise, and limited qubit scalability, which is under research. And I wish to tell about foundations of quantum mechanics. You know that digital computing is a fundamental unit for classical computation. We have two distinct states such as 0 or 1, and something like a switching the light on and off state represents 0 and on state represents 1. Qubit is a fundamental unit of quantum computations, but we have realized several state in quantum computing, such as superposition of state, which is represented by in terms of vectors. Alpha 0 state plus beta 1 state, where alpha and beta are probability amplitudes actually. Based on the amplitude values, the state will be varied. And the alpha squared plus beta squared should be equal to 1. That is, in probability theory, the summation of all the probability values is equal to 1. No? In a similar way, we have 1. Which enables a simultaneous computation of multiple states, which offer massive parallelism. This is the simple illustration of digital computing and quantum bit. Okay, we have particle or wave particle around the sphere. We have 0 kind of state and 1 kind of state. And also the state in between 0 and 1 will be represented as a superposition state. So we can represent state of a quantum system by using Dirac rotation, bracket rotation. Qubits are represented in terms of Dirac notations, or a Ket notation. Here 0 represents the quantum equivalent of the classical 0, and 1 represents classical 1 value. The superposition is represented in terms of bracket notations, alpha 0 state plus beta 0 state. Based on the amplitude value, the different state will be achieved. So already I told about these things. There is probability of measuring 0 and probability of measuring 1. If alpha value is 0 means it closely associated with 1, and beta value is 0 means is closely associated with 0. Okay. The key example is psi bracket equal to 1 divided by square root 0 plus 1. Here alpha squared is equal to beta squared equal to 0.5, which is equal probability of measuring 0 or 1. Okay, the probability of 0 is also 0.5, probability of 1 also 0.5. It is the intermediate state or superposition state. We can represent qubit in terms of block fair visualization. A Bloch sphere is a geometric representation of a qubit quantum state. Qubits are represented as points in the unit sphere. This is a point. Qubit is a point in unit sphere. Here we have three basic components. There is folds, equators, and the axis. So folds may be a north pole, which is represents a zeroth state, and south pole is a one state. Here, equator is something like a superposition state, which is represented like 1 by square root 0 plus 1, which is the 0.5. There is a superposition state. The probability of alpha is 0.5, and probability of 1 is also 0.5. Here, axis X, Y, Z represent the phase and amplitude relationship. Okay, and also Z axis is a computational basis. X or Y axis represents the phase changes. So to change the phase of the axis, we use X. If we wish to change the computational basis, means we change the Z axis. So that is something like an imaginary axis. So quantum state can be represented as that is a geometry representation, that's cos theta by 2, which is a zero representation, and for one representation we represent e power I psi sin theta by 2. So if you wish to represent in terms of angular values, means we can use this. So here theta represents the latitude and psi represents the longitude. The main advantage of using Bloch sphere representation is we can visualize the quantum state superposition and transformations, and also it demonstrates the impact of quantum gates, whether rotate along the axis or not. We can illustrate how the transition is happened between the state during computations. So superposition state, as I said already, we represent by using coefficient values alpha and beta, which is something like a coin, which represent, which resembles coin toss analogy. Actually, classical coin shows the either gets get means 0, or head means 1, or tail means 0 after a toss. But in qubit representation, it's like a spinning the coin that exists in a mix of heads and tails. Okay, so there is a analogy by using the coin toss. Next, quantum entanglement, which is not realized in digital computing, which is a concept where the states of two or more qubits become interdependent. The state of one qubit may be associated with another qubit, such that measuring one qubit instantly defines the state of the other, regardless of the distance. This is a significant aspect of quantum computing. It is a foundation for quantum teleportation and quantum communication, and also it enables parallelism and strong correlations, which enhances the algorithmic efficiency in terms of running time. And while analyzing or identifying the state, we may face superposition collapse. That is, when a qubit in superposition is measured, it collapses at one of this basis state, whether a 0 state or 1 state with probability determined by alpha square and beta square. The by using gate operation, that is, we can measure the at the end of quantum algorithm to extract results, and also gate operations manipulate qubits without collapsing superposition, which permits computations before measurement. Now I wish to discuss about quantum gates. Actually, quantum gates are the building blocks of quantum circuits. Actually, by using the collection of gates which is associated with the links or connections, we form quantum circuits. Quantum gates are unitary operations that manipulate qubits in a quantum circuit, which is analogous to the classical logic gates in digital circuit. They operate on quantum states, which may be a 0 or 1 and superposition state, which is governed by unitary matrices. That is, we can represent quantum gates in terms of matrices, and also we do vector operations. The key characteristics of quantum gates is which we can operate on single qubits or multiple qubits. Um, and also we can enable operations like superposition, entanglement, phase shifts. So here I'm in a position to compare digital logic gates with quantum gates by using several features. The basic unit is 0 or 1 in digital logic, but in qubit we realize 0 or 1 or superposition state. As I already said, state representation are deterministic in classical computer, but in quantum computer is probabilistic. Here, the operations are irreversible in classical logic gates. That is, irreversible means that the data may not, by using the that is outcome, we can recover the data by using the quantum gates, but it is not possible with logical gates, which is irreversible. Example gates operation is AND gate, OR gate, SR gates. But in quantum gate, we use unitary matrices. The information flow is unidirectional in digital logic, but in quantum gates, we realize bidirectional transformation. Example logical gates include AND or NOT, but in quantum gates, we have several examples: Hadamard card, Foley X, C naught, and T gate. These are the example for quantum gates. I will explain one by one. So quantum logic is represented by using that is vector representation. I mean matrix representation, which is similar to digital logic only. Here, a classical NOT gate flips 0 to 1 and 1 to 0, which is achievable in quantum logic by using the Foley X gate. Here, when you input 0th state means it will output 1 state. So, in quantum computing, Foley X gate is equivalent to NOT gate in digital logic. Okay, which is represented by using matrix. A Foley X gate flips the state of a qubit, that is 0 to 1 and 1 to 0, which is represented matrix format. Okay. So for when you give 0 means it will give 1. So 0, 1 is a one matrix, one vector, and 1, 0 is another one, which is correctly represented as a matrix here. So for 0, I told already 1, 0. When you give 0 means it represents 1. For 1 means if we get 0, 1. So if you combine these things means you will get matrix like this, result like this. For if you input 0 means you will get 1. If you give input 1 means you will get 0. Okay. So we do tensor product here to achieve when you input 0, 1 means you will get 1, 0. When you input 1, 0 means you will get 0, 1. So we apply tensor 0. So tensor product, for example, you just multiply here, okay, and multiply here. Okay, what do you get? 0. That is mentioned here. Okay, next you multiply 1 with 1 and 0 with 0. You will get 1. That is mentioned here. So one representation is mentioned here. Already I told, no, for 1 we may represent as 0 for a quantum logic. Okay, so this is the matrix notation for Foley X gate, which is equivalent to NOT gate. Okay, so tensor product multiplication, something like a matrix multiplication. Okay. And the unitary property of quantum gates that I wish to mention, a matrix U is unitary if U plus U equal to identity matrix. Okay, when you apply unitary operations, there is a U plus is a conjugate transport of a given matrix. Okay, and I is the identity matrix. Okay, just to apply conjugate transpose, I mean tensor product with U and U plus. U plus is a conjugate transpose of a matrix.
I have a doubt.
Just a minute. Tell me, ma'am. Tell me, ma'am.
I have a doubt.
Tell me, ma'am. Tell me. Ask question, ma'am, please.
No, sir.
Okay. No problem. So, if this is a matrix actually, given matrix, the conjugate transpose is applied to the matrix. You just perform multiplication, you will get identity matrix. So, the benefits of using unitary property, I mean, unitary property is we can ensure reversibility of quantum operations, and also it maintains the total probability as alpha squared plus beta squared equal to 1. Okay. Next, quantum gates operates on unitary transformations, and we can apply, we can change the superposition with the help of superposition. We can operate quantum gates, and also we can change the phase. Changes of phase also we can operate quantum, and also we can make use of integral properties to achieve quantum gates. There is quantum. You can operate quantum gates. That is, we can achieve operations like NOT, XOR logic, and we have several operations, specific operations like controlled NOT, control NOT, etc. The key points here is we can transform the state, and also we can perform multi-qubit operations by using quantum gate, and also we can achieve reversibility. But reversibility is not possible with digital computing. Already I told about the states transformation is achieved by using gate, I mean Hadamard gate, which creates superposition actually. And also we can do multi-qubit operations. Multi-qubit means we can single qubit representation represents 0 or 1. 0 or 1. 2-qubit operation, which is represented as 0 0 0 1 1 0 1 1, which is similar to see in that you realize in digital gates. Okay. And also 3-qubit also available. That we realize in 3 bits. We have 3 bits for qubit representation. It starts from 0 0 2. It ends with all ones. Okay. In controlled not 2-qubit operations, when you apply 0 means you will get 0 0 0 means you will get 0 0. When you apply 1 0 means you will get 1. Here, why you get 1 1 for 1 0 means here the control signal is enabled. Okay. So if control bit is 1 means it will be there is 0 state will be converted into 1 state. So there is the concept again controlled not. There is an example for 2-qubit operations. So here the role of quantum algorithms in CNOT gate, that is contributions towards the development of quantum algorithms. Actually, quantum algorithms are the sequence of gate operations which aim to solve specific problems. Here the gate gate is used for creating the superposition actually. Here Hadamard gate generates the equal probability state. Okay, that is also one building block. Actually, if you wish to develop quantum algorithms, means quantum gates plays a vital role. For example, for creating superposition, we use Hadamard gate. If you wish to do entanglement state, means we use CNOT gate, which create entangled state for the parallelism. And also, if you wish to change the phase, means we use phase gate. That is, example for phase gate is T gate. Next one is identity gate, which ensures no change in the qubit state actually, which also act as a just a minute. Identity gate act as a do nothing operations, which does not change any qubit, and also it's beneficial for timing adjustments or maintaining qubit circuit structure. This is a example for 2 by 2 identity matrix. So identity matrix means do nothing operation. Okay. The applications of identity gate is, it is act as a placeholder for quantum circuit, and also it aligns execution timing across multiple qubits, mainly used for testing and debugging purposes. Next one is poly X gate, in terms of that is, we can regularize the NOT operation in qubit digital quantum computing by using poly X gate, which is represented as a matrix format 0, 1, 1, 0, which is looking like a identity matrix. And also, when you visualize Foley X gate in Blocksphere, actually Foley X gate performs the 180-degree rotation around the x-axis. Okay, so it moves the state vector directly to the opposite side of the sphere. Okay, this is the concept behind Foley X gate. Application is used to what is a foundation for building the other quantum gates, mainly used for state inversion as well as flipping. Next gate is Foley Y gate. Actually, the purpose of Foley Y gate is simultaneously flips the bit and applies a phase shift. It also flips the bit as well as the phase shift. So if we so it combines the properties of Foley X gate as well as Foley Z gate actually. If you wish to change the 0 state to 1 state means we can use Foley X feature. If you wish to change the phase means we need to use a Foley Z gates. So this is a matrix representation of a Foley Y gate. And when you visualize the Foley Y gate, actually Foley Y gate performs 180-degree rotation around the y-axis of the Blocksphere. It rotates the state vector between the 0, 1 with a phase vector. The main application of using Foley Y gate is used in specific operations where both and bit changes are necessary. Mainly it is used to used in error correction and quantum algorithm design. Next gate is basic gate is Foley Z gate, which does not change any value in zero state, but it flips the sign of 1 actually, 1 state. It does not affect the probability of a measurement outcomes, but changes the phase. This is the representation of a Foley Z gate. So just it changes the sign of a 1 state. If you wish to represent a qubit state in terms of vector means, you can mention as Z psi equal to alpha 0 minus beta, because we have changed the sign, no, so it is minus mentioned here. So when you visualize the Blocksphere, I mean Foley Z gate in terms of Blocksphere, it performs a 180-degree rotation around the Z axis. So it affects the phase of the state without altering this position. Okay, position in the XY plan. The main advantage of using Foley Z gate is it is used for phase correction, and also it is integral to gates like Hadamard and S gate. It is used in quantum error correction and stabilization of quantum states. So next one is Kadamat gate, which is mainly responsible for introducing superposition of qubit state, which converts 0 state to 0 plus 1 divided by square root 2, and 1 state to 0 minus 1 square root 2. Matrix, in a matrix format, we can represent Kadamat gate as 1 divided by square root 1 1 1 minus 1. Okay. So you know that the imaginary value, the factors are represented as alpha plus or minus beta square root 2. Mainly, the Kadamat gate is responsible for rotating the qubit state halfway between the z-axis and x-axis, it creating the equal superposition. The application of Kadamat gate is used in quantum interference and entanglement generation, and it is essential for quantum algorithms like Groover search and source factoring. So this is the simple example for quantum circuit which involves a Kadamat gate, okay, single qubit gate. And this is summary of the gates: identity gate, X gate, Fowley X gate, Fowley Y gate, and Fowley Z gate, and Kadamat gate. So these are the basic gates we use in single qubit. And for phase changes, we use phase gates, that is S gate and T gate. S gate is responsible for adding the phase 90 degree to this one state. This is the example for S gate. Zero in zero state, according to zero state, no changes happen. In one state, we have 90 degree phase shift. Okay, so one will be transformed to I1. The matrix representation here mentioned here. In place of 1, we realize I here because we have changed the 90 degree phase. And another one is T gate. It adds a phase of, that is 45 degree. I mean, yeah, that around 45, 22.5, I think so, 22.5 degree. Also represented 5/4 degrees to the state. Here, the zero state will not be changed, but one state will be changed to e power I 5/4 1. Okay, so this is a T gate representation, which is represented as a matrix. So for a qubit, S gate is represented as a vector like alpha 0 plus beta I 1, and T gate represented as alpha 0 plus beta e power I 5/4 1. Okay, this is these two are superposition state only. Okay, these are used to introduce superposition state. So the applications of these gates, phase gates, is which is responsible for phase shift in quantum circuits, and also S and T gates are critical for universal quantum computation. It is mainly used in algorithms which requires precise phase control. So this is a simple example which is for S gate and T gate, mainly used for phase changes. Next one is controlled gates. Control gate, one example is control NOT gates. That is along with the input, we have control line. Okay, which you studied in electronics department. We have input vector. Along with the input vector, we have control input. If control input 0 means no changes will happen for the output. When control bit is 1 means the changes, the output may have changed. Okay, so conditional actually one of the controlled gate is C0 gate. Here we do conditional flip operation. If you flip the target bit only if the controlled bit is 1. Okay, this is truth table for controlled NOT gate. For example, actually the input is 0 state. Okay, when control input 1 means the output will be flipped to 1. Will be 0 will be changed to 1. If control input 1 and input is 1 means this 1 will be transformed to 0. So this is a example for controlled NOT. Along with the input, so along with the Foley X gate, we are introducing another one that is controlled input to get an output. So this is the example for control NOT. So control NOT actually resembles XOR gate. Okay. For example, this consider you have input 0, 1, and control line is 0, 0. Okay. So this is controlled input. This is an actual input. Okay. This is the output. Consider. When you have 0, 0 means the control 0, actual output also 0. When you 0, 1 means control input 0 and output also 1. When you have 1, 0 means, so control input, since control input is 1, output will be changed to 1. Okay. And if you have 0, control input is 1 and actual input is 1 means output will be control input 1 and output will be flipped to 0, which resembles XOR gate. No, when two input are different means output will be 1. See here, I have a box here. When two inputs are different means output will be 1. So control NOT gate represents, resembles XOR gate in digital logic. Okay. So this is represented as a matrix way. Matrix analysis representation. And in Blastware, it acts as a Foley gate on the target qubit when control is with 1. Already I told Foley X gate. This is the example for CNOT gate circuit. We supply inputs and apply Karamat gate here to identify superposition state. And the next control jet gate. It also main purpose of using controlled jet gate, controlled gate jet, also shortly called as GJet gate. It adds a conditional phase flip operation. Okay, it flips the phase of the two qubits state 1 1. When you control bit is 1 means the phase is changed to negative, that is minus 1 1. When you give 1 1, output will be changed as minus 1 1. Other state will not be changed. This is the example for CJet state. Matrix format, it is represented as matrix format. As here we have minus 1 because for 1, for 0 0 we have data like this. For 1 we have data like this. For 1 0 we have data like this. For 1 1 we have changes in state, that is minus. So phase shift is changed. So phase changed, so minus 1 will happen here. This applies a Foley jet gate on the target qubit when control bit is 1. This is the representation of graphical representation of a CJet gate. So mainly we use CNOT gate for creating entanglement and CJet gate for phase-based quantum operation. CNOT gate is mainly used for error correction and CJet gate is mainly used for controlled phase adjustments. Next, I wish to discuss about composite and universal gates. Already I told about single qubit operation and controlled gates. Now I wish to tell about along with single qubit operation, I wish to tell about two qubit operation and 3 qubit operations. Mainly, if you wish to perform multi-qubit operation means we use tensor products to combine gate operations. Multi-qubit system are represented by tensor product of individual qubits. For 2 qubits, we represent the qubit, the data as psi equal to psi 1, tensor product psi 2. So if you have 2 qubit means first qubit will be considered U and second qubit will be considered V. In matrix, we represent as U11V, U12V, U21V, and U22V. So I explain with an example. If you have two identity matrix and you wish to represent tensor product means just to have matrices, identity matrices, and perform tensor matrix multiplication. So just apply 1 1, you will get 1, and 1 0, you will get 0, and 0 0, you will get 0, and 0 1, we will get 0. Something like a matrix multiplication. So finally, you will get identity matrix like this. Okay, this is the tensor product between 2 qubit system. It's identity matrix, and this is another 2 qubit system. That is, you are applying tensor product between the Kadamard gate and identity matrix. So you will get matrix like this. The main advantage of using these combined gates is it enables simultaneous operation on multiple qubits, and is also used in constructing the entangled states and implementing multi-qubit gates like CNAT and CZ. Mainly used for building the large-scale quantum circuits. Now I wish to tell you about universal gate sets. Actually, a universal gate set is a set of quantum gates that can approximate any unitary operations on quantum system, mainly useful for implementing the general quantum algorithms. So universal gate sets, the example for universal gate sets is CNAT plus single qubits. Here, Hadamard gate and phase gate, Foley gate case compared with the CNAT gate can form any quantum circuit. Mainly, we use Hadamard gate for creating superposition, CNAT gate for entanglement, and phase gates for phase rotations. And also, we have Toffoli gate, also known as controlled NOT gate. Here we have two control lines actually. Okay, based on the control gate, control lines, two control lines, we create control NOT gate, which resembles a NAND gate actually. A 3 qubit gate that flips the target qubit. Only both control bit is 1. Okay, output becomes 1. Output becomes flipped, will be flipped if two control bits are 1. It forms a universal gate set for classical reversible computation, and also it combines single qubit gates and achieve quantum universality. The main significance of circuit design is flexibility. In quantum computing, we have flexibility. That is, we can create universal gate sets that enables implementation of any quantum algorithm from basic computations to complex simulations. And also we can do standard operations by using the universal gate set to improve reliability and performance. And also we can use it for error corrections. That is mainly we use error correction mechanisms for creating the fault tolerant quantum computing. And also it is under research. So control NOT something like a NAND gate, which we have two control bit and one target qubit. This is the matrix representation of control NOT gate. So the control NOT is reversible one. That is, it preserves all input informations. And also it forms a universal gate for classical reversible logic. Mainly, it is a crucial building block in quantum algorithms such as quantum error corrections. So we can create a complex quantum circuit by using Toffoli gates, and also we can do binary arithmetic operations such as addition and multiplication by using this. So this is example for control NOT gate. So here when we have control input is 1, to control input is 1 means this input will be flipped. Okay, its state will be changed when both the input are 1. Control input are 1 means the output will be flipped. So that is represented here. 0 1 will be changed to 1 1 0. So for all the data, the input will be same, output will be same. Next one is Fredkin gate. It is also called as controlled swap gate. It acts on 3 qubits only. We have 1 control bit and 2 target qubits. Actually, C swap gate is responsible for swapping the 2 target qubits only if control bit is 1. It leaves the target qubit unchanged if the control bit is 0. This is example for matrix representation for Fredkin gate. The advantage of using this is it is responsible for reversible computing. This is conserve information during computation, and also mainly useful for error correction and multiplication, so multiplexing and quantum logic design. So these are the examples for quantum gates. These gates are single qubit, 1 qubit. These are 2 qubit. These are 3 qubit operations. So the physical relation of quantum gates is basically relying on the principle called superconducting qubits. Actually, supercomputing qubits are based on the superconducting circuits that exposes the quantum behavior at cryogenic temperatures. Actually, we implement that is supercomputing qubits by using Josephson function, which permits control over quantum state by manipulating electrical currents and magnetic flux. Mainly, it operates on quantum regime by energy levels of accelerating currents in superconducting loops. The use cases for superconducting qubits is we can perform quantum computations. We can use it for quantum machine learning. That is, we can perform computations for identifying the vectors, optimal vectors to perform data classifications, and also we can try to avoid the local minima by exploring the several set spaces in machine learning. That is main advantage of using quantum computing in machine learning. We can achieve computationally efficient system, and also we can reduce the error quickly with the help of quantum machine learning. And also we can perform scientific modeling. That is, we can simulate quantum systems, which is mainly useful for bioinformatics, material science, etc. So example is IBM quantum processor. Actually, IBM uses superconducting qubits. Examples include 127 qubit processor, IBM Osprey. We have 400 qubits, which demonstrate advancement in scalability. The key advantages of IBM system is it is a scalable architecture and also computationally feasible one. The challenges of IBM system is it requires ultra low temperature, and also error rate and decoherence still limit the large scale implementation. Still, it is under research. Another one is ion trap quantum gates. Ion, like superposition gate, ion trap quantum gates use charged particles trapped in electromagnetic fields. Ions are typically beryllium and ytterbium, manipulated with a laser to control quantum gates. We can perform quantum gate operation with the help of laser pulses that induce transition between ions energy levels. So this is the simple animations. I mean, images resembles ion trap quantum approach. So ion trapping in ion trap approach, we have ions which are confined in a vacuum chamber using electromagnetic field. We can control the state by using the laser beams, and also we can manipulate the state, internal state, by using that. We can achieve two qubit gates by coupling the motion of two ions in the trap using collective motional state. The advantage of using this ion state quantum approach is you achieve high fidelity, and also we can achieve a highly scalable system. The challenges of using this approach is when number of ion increases means it becomes more difficult to maintain control. The setting up of this system is also highly costly and complex one, because it requires high precision lasers, vacuum systems, and also we face challenges in interfacing and error corrections. Next gates, quantum gates is photonic quantum gates. Here we use particles of light as a qubit in quantum computing, which makes use of properties like superposition and entanglement. Photonic quantum gates manipulate quantum informations which carries using optical devices like beam splitter, phase shifter, and mirrors. The main advantage is which involves no decoherence, and also we achieve easy transformation. Just a minute. Yeah. Yes, CJ gate is opened as 4x4 matrix only. I have mentioned in PPT, that is correct. Yeah, other gates are out at only on one bit. Okay. Poly X gate, poly Y gate are represented in terms of only one gate. That is correct. That correct, Venkata Subramanian sir. Yes, sir. I didn't watch this chart. That is correct. Your point is correct. Example for this, there is photonic quantum gate is linear optics quantum computing. Actually, linear optics involves manipulating photons through linear optical elements. Examples involves beam splitters, phase plates, and mirrors. Mainly, we implement this kind of quantum gates by using the CNOT, Hadamard gate, and phase shift on photons. So the example operation include photon quantum gates is beam splitter, which is responsible for creating the superposition state, and phase shifter, mainly useful for applying phase changes to the photons. And also we can we can find the association communication between the qubit state by using the entangling gates. We use technique like Congo-Mantel interference to build the entanglement between the two photons. So advantage of using this is scalability. Photon can be generated, manipulated, and detected using several technologies. but also we can achieve entanglement by using quantum communication network. And also it is high fidelity one. There is photons are less susceptible to errors when compared to laser approach, ionics approach. Challenges are we face nonlinear interactions since photons do not interact strongly with each other. So we face nonlinear interaction. There is an issue. The detection efficiency is also low. Efficient photon detection at high speed levels prevents a challenge. So error correction methods are still under research in photon-based quantum gates. So other implementation which is related to quantum gates are topological qubits and neutral atoms, which is under research. So topological qubits relying on anions and also exotic particles which exist in two-dimensional spaces. And also we can create a large-scale system. The challenges with respect to topological qubits is complexity, which requires precise control and manipulation of excited and anion particles. And it is under development stage. It is under research. There are many organizations like Microsoft doing research in this field. Next one is neutral atoms. Actually, neutral atoms are trapped using optical lattices, which is built by laser fields, where atoms are manipulated by laser pulses. Here, laser pulses are used to manipulate or change the behavior of atoms. Here, each atom acts as a qubit with internal electronic states representing the quantum information. Here, the advantage is scalable one. We can create scalable system, and we can enable the system which is less sensitive to environmental noise. Okay. So the basic quantum system, which is affected by environment, but we can develop the system which is less sensitive to the environment by using the neutral atom. Challenges is which requires complex and high precision laser to control the atomic state. Entanglement generation, that is communication across the state, is a challenging one. And also some neutral atom gates relatively slow operation times, which limits the use in practical application, used for practical applications. So there are several error correction techniques which you realize in quantum gates. The main purpose of using quantum error correction is maintaining the integrity of quantum information during computations, which is essential for problem solving, computers problem solving, which is for sequential algorithm as well as parallel algorithms. So gate operation must be fault tolerant to ensure the long quantum algorithms remain accurate despite errors in qubit state measurements and interactions. So we use for error correction, we use surface codes. The main purpose of using surface code is, in surface code we use a 2D grid of physical qubits to encode logical qubits. Actually, we represent physical qubits as a grid, and errors are detected using syndrome measurements. If errors are detected, means necessary action can be done to recover the logical qubit. So this is the representation of a error correction codes. So advantage of using this is highly tolerant to errors, and also it requires only local interaction between qubits, and we can achieve high scalable systems. Challenge is it is large overhead. Surface codes are requires many physical qubits, which usually encode a single logical qubits, which increases the complexity of the system. Now I have to show some animations which expresses the importance of the quantum computing. Just a minute. I think we are visualizing this one.
The laws of physics that apply in the microscopic world at the
We're able
level
to view
of
the
individual atoms,
screen.
individual electrons, elementary particles, where physics is qualitatively different than what we experience in our everyday lives. You ever been to the beach? You see waves coming in. Why do the waves have characteristics? Speed. That's all classical physics. Send a rocket to the moon. There's no quantum physics in that.
We're discussing right now quantum world, which is at the very smallest scales. The elements of reality down at that level are not described by what we're used to, which is the momentum of something or the position. If you were to go and ask the same question at the microscopic level, at the quantum level, then things break down. So things are different there.
And that's a big part of why we're interested in this whole subject. Can we take this quantumness of the microscopic world and blow it up to larger and larger sizes, manipulate them in a way which is highly controllable to get them to do what we want them to do? If you have a quantum system, that quantum computer can do things, can perform tasks that we couldn't hope to perform with ordinary digital computers. You can't dream of doing it. So when we think about how quantum information is different from classical information nowadays, we're thinking about this intrinsic randomness, the uncertainty principle, and also about entanglement. You know, classical information we can express in terms of bits. You can take any amount of information and just write it as a string of bits. And in the quantum case, we call them quantum bits or qubits, and they're different from ordinary bits in some fundamental ways. So a classical bit, I can write a 0 or a 1 on the table and everybody can look at it in the same way. But in a quantum bit, there's more than one complementary way to look at it. So you can kind of picture it this way. You've got a box and you can put an object in the box. In the quantum case, there's more than one way to open the box. And you've got to make a choice. If you open door number 1, you'll never know what would have happened. It cannot be known what would have happened if you had opened door number 2 instead. Those are incompatible things. That's something really new compared to classical physics. That's what I mean when I say it's really intrinsic randomness. It's not that there's some record somewhere, but you haven't looked at it yet. There's no record. It hasn't been decided yet whether it's going to be 0 or 1. It's not until you make the observation and open the door that it becomes the value of this bit. Maybe it's a 0, maybe it's a 1.
The randomness comes from the ability of quantum states to be in a superposition, to be both in the state of 0, of definite, like say spin up or some like particle, and
Hello, excuse me. Excuse me. Excuse me.
right, and you can like put together, and you can think of having half of a 0 and half of a 1. So whenever you measure it, you will end up getting half of the time the 0 and half of the time the 1. So superposition is fundamental for that randomness.
If I flip a coin, I don't carry coins in my pocket anymore, or I'd flip one. I flip a coin, and then I cover up the coin as soon as it lands. You don't know whether it's a heads or a tails, but it's either a heads or a tails. We just don't know yet. That's not a superposition. That's a probability distribution. But if we have the most complete description of the system that is possible, compatible with quantum physics, like when I prepared the state and when we open door number 2, we don't know whether it was a 0 or 1, that's superposition, because that's really intrinsic randomness instead of probability associated with ignorance.
So it takes two to tango in quantum entanglement, right? You cannot just have a single qubit and say, oh, it's entangled with what? So you need 2 qubits at least.
The reason these quantum correlations are different than classical correlations is because we have these distinct, incompatible ways of observing the system. Classical systems can be correlated. We can flip 2 coins and they're either both heads or they're both tails. No big deal. But there's just one way to look at that coin. The qubits are different. We have these 2 incompatible ways of looking at them. They have 2 ways to be correlated, either the same or different for 2 different sets of doors. Those are altogether 4 possibilities, and that means the correlations are richer, they're more interesting. And the richness of the correlation increases very markedly as you increase the number of parts or add additional qubits. You know, if you have just a few hundred qubits and you want to write down a complete description of all those correlations among those qubits in terms of classical bits, you'd have to write down more numbers than the number of atoms in the visible universe.
It's one of these things like, I don't know if it was Faust that said it, that achieving perfection is hard, but remaining perfect, that's impossible. A lot of what we're trying to do also create things that are stable, right? Because you can have the most exotic quantum state, but unless you can probe it, measure it, evolve it in some way that you want, steer it, it's going to be useless.
There's a central problem, and that is if you're running a quantum computation, if you're performing a sequence of operations, processing quantum states, that has to be very well concealed, not just from you and from Spiros and from me, but from the whole outside world. Classically, there'd be nothing wrong with looking in every time step what the state of the computer is. That wouldn't prevent the computer from getting the right answer. But quantumly, if we keep looking at the computer, that will destroy these delicate superpositions. It's a secret computation. Until the end, when we're finally ready to get the result out, we make a measurement, and then it's okay to tell everybody what the outcome is, to broadcast it to your friends. So we can't be looking at the computer while it's performing the computation. If we ask it afterward, what did you just do when you factored that huge number, it should say, I don't remember, because there was no record left behind of what it was doing at intermediate stages of the computation. And this is what makes it so challenging, because we can't allow any leakage of information from the computer to the surroundings. That would destroy the quantum computer. That's what we call decoherence. It's the big enemy. There's a whole quantum world out there which is largely unexplored, because it's only now, within the last decade or so, that we are developing the technological capability to scale up quantum systems, to manipulate them, and we're not exactly sure what that's going to lead to, but we think it's exciting. And I do get excited.
I hope you understood. You got to know about the basic concept behind quantum computing. Now I wish to continue with the session. So now I continue here. That is, with this I stop this session. That is first session of today. The applications of quantum gates is realized in machine learning. Actually, quantum computing is expected to enhance the machine learning operations by making use of quantum gates to process information fundamentally in different ways, which is able to handle a huge amount of data. And also we can increase the speed of for certain tasks like optimization, mainly using in neural network and the regression models, and also pattern recognition, and also data classification. The key roles of using quantum gates and quantum enhanced machine learning model is we can achieve superposition for parallelism. Quantum gates such as Kadamard gate, which enables superposition, and also the implication of using this kind of gate is quantum enhanced ML models can simultaneously explore several hypotheses, and also we can use it for feature extraction, which leads to faster conversion and better exploration of complex data spaces. Example includes quantum model can represent all possible state of a data set in superposition and process them parallel, which allows the speeding of tasks like clustering or classification. And also we can use it for feature correlation. Uh, Quantum methods like CNOT and SWAP can create entanglement, which links qubits in ways that classical system cannot. And also we can find the association between the features by using the quantum entanglement. I mean, CNOT and SWAP gates. The implication here is entanglement permits quantum ML model to capture complex correlation or association between the features. Features are input vectors. The example includes quantum enhanced neural network can make use of entangled qubits, which is used to represent the interdependencies between the features that are more effectively than classical neurons. That is, we can find the association between the features so that we can effectively make the classification as well as prediction task. And also we can develop hybrid quantum classical models. In hybrid quantum classical models, quantum gates perform quantum part of the computation, that is data encoding, superposition, entanglement, while classical computers handle the classical data processing and optimization task. The outcome is this approach combines the strength of the quantum computing and in processing quantum information with flexibility and the power of classical computers, which leads to faster learning algorithms. Example includes variational quantum eigensolver. Mainly, eigensolver is used for linear transformation, used in quantum machine learning for data classification, which combines quantum gates for state preparation and classical optimization for parameter tuning. So parameter tuning is very fast when we use quantum computing methods. So thank you for the opportunity. I will start next session, that is involves quantum circuit in after 10 minutes.
Okay, sir. Thank you.
Shall I start after 10 minutes, sir? Do you have any queries?
Participant, if you have any queries, you can ask. Kanimut sir.
Sir, tell me, sir.
Sir, if you have any clarification, you can rectify it. Otherwise, you can go with next session, sir.
Okay, sir. Shall I continue with the next session, sir?
No, sir. Just take 10 minutes break
10
for
minutes, 10 minutes
next
break.
session.
Okay,
Yeah.
sir. Okay, sir. I start at 7:30, sir.
Yeah. Okay, sir. Fine.
Okay, sir. Okay, sir. Thank you.
Participant, be on 7:30 for next session. If you have any queries, you can send your queries at
Okay,
chat
now
box.
we are leave, sir, this meeting.
Sir, kindly share your queries in chat box.
Gopi sir, shall I start the session, sir?
ஓகே சார், ஸ்டார்ட் பண்ணுங்க.
Yes, sir. Thank you. Good evening, participants. I continue the next session titled Quantum Circuits, Foundations, Design and Applications. Before getting into the session, I wish to answer for the participants' questions. One participant asked, what are the books to be followed to learn about quantum computing? I suggest 3 books. Please make a note of it to study the basics of quantum computing, which is highlighted here. You can take a note. And also, we can make use of the tools. Another participant asked, like, what are the software tools used for quantum computing? These are the software tools as used for simulating or making use of quantum computing facilities, that is Project Q, CERC, Q control, and so on. Can add one tool called CSKit, QSKit. I saw the demonstration for implementing quantum machine learning algorithms using Python. By using Google Colab, I demonstrated. So we can solve several classifications of the prediction problem by using the this tool. So we can use PennyLand tool for implementing quantum machine learning approach. I will explain that as a demonstration, since you have asked for demonstration. So closely I have worked with quantum machine learning, so I demonstrate that. So these are the 2 questions asked. So one person asked a question: which kind of qubits can be used for implementing our approach, solves our problems like that? The answer is each qubit, each gates contains pros and cons that is specific for solving the problems. For example, if you use single qubit, means we can achieve, we can implement, we can resemble NOT gate, XOR gate, and so on. That is specific for the operations, whether you are using a single qubit or 2 qubit, 3 qubit. If you wish to solve the problems by using quantum algorithm, means we can use any one of the technique. Quantum image representations. So one participant asked, like, suggesting implementation techniques for quantum image representation. So I didn't come across quantum image representation. I will let you know what are the implementations that can be useful for representing the quantum image. Okay. Thank you, Nikyam. I will let you know soon. Now I go to the overview of this session. That is, here I wish to introduce fundamentals of quantum circuits and design, and I will discuss about algorithms and applications of quantum circuits. Then I will explore about the challenges and future direction, and finally conclude with the real world applications and case studies. So these are the tools we can use it for quantum computing implementation. But I worked on QSKit and Pennyland for implementing quantum machine learning. So because my subject area is, area of interest is machine learning. So I worked on that field. Now I wish to discuss about fundamentals of quantum circuit. The purpose of using quantum circuit is we face several issues in digital computing. That is, challenges involves complex problem solving like paternization, optimization, and large scale simulation. We face several issues in that, so we get rid of that. We use quantum circuit. Actually, quantum system can solve several problems exponentially faster than classical system. Example is SARS factorization algorithm and searching algorithm. This is a representation of quantum computer and classical computer, which I already told about this. So mainly the quantum circuit is responsible for designing and executing quantum algorithms using quantum bits, which operates on quantum principle like superposition and entanglement. The potential of quantum circuit is which is mainly used for solving cryptographic problems, material science, and machine learning. So now I wish to come across there is milestones in quantum. The quantum mechanics. There is historical overview of quantum computing. Early 1900 itself, quantum computing coined by Planck et al. During 1980s, Richard Feynman proposes the idea of quantum systems. They simulate physical processes which act as a foundation for concepts of sort of quantum computing. During 1994, Peter Saar develops the SARS algorithm for efficient factorization and demonstrate the quantum computing potential. Key contributors involved in this field is Richard Feynman, David Church, and Peter Saar. Already I told about the quantum gates. These are all useful for constructing the quantum circuit, such as single bit Q gates, 2-bit Q gates, and 3-bit Q gates. In terms of single qubit gates, we use Foley gates, Foley S gate, Foley Y gate, and Foley Z gate. Foley S gate resembles NOT gate, and Foley Y gate combines bit and phase flips. And the Foley Z gate is responsible for flip the phase of 1 to -1. Kadamot gate is responsible for creating the superposition state, and S gate and T gate is responsible for phase shift. And in terms of multi-qubit gates, we use controlled NOT, which flips the target qubit if the control bit is 1, and swap gate exchanges the state of the 2 qubits. And mainly in this swap gate, as participant asked the question, in which scenario you can use this kind of gates is, if you use swap gates means we can implement there is a mutation operation in mutation operation in genetic algorithm. I have used this kind of gates in implementing the optimization algorithm, that is quantum genetic algorithm. In quantum genetic algorithm, we have one of the operator called mutation. Mutation, crossover. Crossover, we exchange the state of 2 qubits. So in this situation, we can come up with a new offspring in genetic algorithm. So I have used a multi-qubit there, which I explain later about my research work. I saw the research paper and algorithm also. Mainly I use it for utility mining. Next gate is controlled NOT gate. This gate flips the target qubit if both the control bit is 1. So these are the overview of qubit, single qubit, 2 qubit, and multi-qubit. The quantum circuit model involves input qubits. The input qubits are initialized as defined state, whether maybe a 0 or 1, and we make use of quantum gates, which you can apply operation like superposition, entanglement, and rotations. And next step is in quantum circuit is measurement, which is used to extract classical output and collapsing the quantum state. So how do you represent quantum circuits? By using the wires. Actually, wires represents qubit state as they evolve through the circuit, and we make use of single qubit or multi-qubit gates for solving this problem or constructing this circuit. Actually, we represent quantum circuit. I mean, measure the we perform measurement by using the meter symbol at the end of the each qubit line. So here I wish to discuss about mathematical foundation of quantum computing. We use tensor and Kronecker products for performing the quantum computing. Tensor product combine multiple qubits into a single qubit state. Actually, Kronecker products represent multi-qubit operations mathematically. So this is a single qubit gate. There is a Poly-X gate and Kadamard gate. This is the example for multi-qubit gates. The control knot is a symbol for 2-qubit gate. It represents a matrix. Next, the design of quantum circuits. Here, the task is to prepare a specific quantum state. We can prepare a state, superposition state by using the Hadamard gate. First, we need to start with the initial state and apply the Hadamard gate, which transform the 0 state to a superposition state. Next, we need to decompose the quantum gates. The purpose of using decomposing is we can simplify the implementation of hardware by reducing the complex gates into a sequence of basic operations. The main benefit of quantum circuit is, I mean, the decomposing the gate is we can make circuit compatible with physical quantum devices, mainly support a limited set of gates. Example includes control NOT gate. It is a 3-qubit gate used for control NOT operation. Here, the decomposition can be applied using the single qubit gates and the control NOT gates. Actually, we do decomposition process by using the arbitrary single qubit gates and multi-qubit gates. If you use single qubit gates, means we can use a combination of Rx, Ry, Rz phase gates. If you use multi-qubit gates, means we can reduce combinations of control gates and single qubit notations. And also to perform circuit optimization, we use gate cancellation. The main aim of gate cancellation is to simplify circuit by removing the redundant gates. Example, if you use 2 consecutive S gates, means they cancel each other and get the identity gate. Similarly, gate into jet gate is equal to 1. So we can reduce a gate cancel. Perform gate cancellation by using the simplifications. Next, qubit reordering is another circuit optimization technique, which can optimize the placement of qubits to minimize the number of entangling gates. Example is reordering the qubits to reduce the distance between those that interact each other, which minimizes the gate interactions. Next circuit optimization technique is depth and width minimization. Mainly depth is also called as the number of layers of gates in the circuit, which is minimized by reducing the sequence operation. And width is a number of qubits used at any given time, which is minimized by reusing the qubit and minimizing the entanglement. Next is simulation of quantum circuit. We use tools for simulating the quantum circuit. Already I told about QSKit, which is proposed by IBM. It is a powerful open source framework for creating and simulating the quantum circuit. Another is Circ by Google. It's also an open source library customized for building and simulating the quantum circuit, especially for NISQ, noisy intermediate scale quantum devices. Next tool is QTIP, another quantum toolbox in Python. It focuses on the quantum dynamics and simulations. We can also use Project Q, that is an open source framework for simulating the quantum circuit. This is a simple screenshot creating the quantum circuit by using the Circ tool. Circ tool as well as QSKetch circuit. Here I introduce the parameter by using the parameters function. Here number of input may be given as n equal to assigned by using n equal to 5. The next I can introduce a Karman gate by using the h of 0. It is introduced by using h function, and we can introduce the CX state by using the for loop. Next, we can introduce the barrier, that is something like a registers in between phases by different phases. Okay. And we can measure the output by using the output of the quantum circuit by using the measure function. So this is the code fragment for usually in Qiskit, and this is Circ2. So we face several challenges in simulating the quantum circuit. First one is noise modeling. That is a challenging task. Simulating quantum circuit in classical hardware faces the challenge of noise. That should be resolved by using the error correction and noise modeling to improve simulation accuracy. And also we face efficiency and scalability. Quantum circuit actually grows exponentially with the number of qubits. Simulating large quantum circuit requires high computational power. Now I wish to discuss about algorithms and applications which makes use of quantum circuit. First algorithm is it is Source algorithm, and I will discuss about Grover's algorithm. And also we use other quantum circuits in other applications like quantum cryptography. In quantum cryptography, we use Source algorithm for factorization. Mainly factorization is usually in RSA encryption algorithm for identifying the keys. Next, in quantum optimization, we can use quantum approximate optimization algorithm which solves combinatorial optimization problems, such as machine learning model. We use that. That is to identify the weight factor. And in variational quantum eigensolver is another algorithm used for solving optimization problems in chemistry and material science. And another key application, quantum simulation. We can simulate quantum systems and molecules to study their behavior. Mainly, we realize application in trust discovery, material design, and understanding fundamental physics. Now I used to discuss about algorithms, quantum algorithm which makes use of quantum circuit. Here the problem statement is given a function f0, 1, 2, 0, 1, determine whether f is constant. Okay, that is f of if you supply f of 0 means whether it is changed or not. Whether f is constant if f of 0 equal to f of 1. Are balanced if f of 0 is not equal to f of 1. So this problem can be solved by using quantum circuit. If you use a classical approach, means which requires two queries to evaluate two f at both 0 and 1. If you use quantum approach, means by using Dutch algorithm, means we can solve problem with one query by exploiting the quantum formalism. Here we need to set the initial state 0 and 1, and we apply tensor product between 0 and 1. Next, first step in this is initial state. First step is apply Kadamard gate on both qubits. You will get a value like this for input 0 and input 1. Next step is to apply oracle, that is unitary gate for f. This implements a conditional phase shift on f. If x equal to 0, it does nothing. If x equal to 1 means it applies phase of -1. So again, you just apply Kadamard gate on the first bit. Next step is we need to measure the first qubit. If result is 0 means f is constant. If the result is 1 means f is balanced. So in this way we can solve this problem. Next is Gruber's search algorithm. So here the problem statement is given a block of function, that is we don't know about the nature of the function. It returns 1 for the correct solution and 0 for all others. So we need to find the unique solution for that. You need to find a unique solution for which in an uncertain list of n. If you use classical search, means we require order of n evaluations for searching operation. If you use quantum search, means we can achieve the solution by using square root function, square root running time. So the order of square root of n is less than order of n. So we can solve searching task efficiently by using the quantum circuits. Here, first we need to initialize the quantum state. We need to start with n qubit because we are dealing with searching the element in a n-sized array. So we start with n qubits in the state 0. Then apply Kadamard gate on each qubit to create n equal superposition of all possible state. Okay, like this. Next, apply the unitary operations. The oracle unitary operation masks the correct state by applying the phase flip on the target state. Next, we need to apply Gruber diffusion operator. Mainly, we use this to invert the amplitude of all states, amplifying the amplitude of the solutions. Effectively, we can use this to effectively increase the probability of measuring the correct state by applying the following operations. Next step is repeat oracle diffusion operation. If you repeat oracle diffusion operation, we achieve order of n running time to maximize the probability of measuring the correct state. Finally, we measure the qubit. The correct solution is most likely to be observed. Mainly, we use searching to reduce the running time. Gruber search to reduce the running time. Next algorithm is SARS algorithms for factoring. The main use of factoring, SARS algorithm is we can use it for solving the cryptographic problem. Here the problem is factoring large composite number into prime factors efficiently. You take two prime number and consider by using the composite number we choose two prime number. Which is made those two number, which is essentially used for encrypting the data. If you use classical approach, means factoring the large numbers is infeasible with classic computers. If you use SARS algorithm, means we can easily factor the large numbers in polynomial time. Here, what you do is first we need to construct a perform quantum Fourier transform. Here the purpose of using quantum Fourier transform is You can use it for extracting periodicity in modular arithmetic. First, we need to prepare a register state and apply the quantum Fourier transfer to reveal the period of the modular function a for x mod n, where n is a number to be factored. Next step is period finding. Here we need to find the period r of the modular exponentiation. The period r is important because the factor of n is reduced to the greatest common divisor of a f over r by 2 minus 1 and n. Next, after step 2, we do classical post processing. When you find the period r, we can use GCD to determine the prime factors of n. With high probability, the correct factors of n are extracted in a few iterations. It is running time, polynomial running time. Here in SARS algorithm, we use 3 basic components, that is quantum register, quantum Fourier transform, and modular exponentiation. Quantum resistance is useful for introducing the superposition of possible solutions, and quantum Fourier transform performs a quantum Fourier transform to register on the register to reveal the periodicity. Modular exponentiation is used for evaluating the f over n mod n efficiently. Next application is quantum teleportation protocol. Actually, quantum teleportation permits the transfer of quantum information between 2 distance locations without physically transferring the qubit itself, using entanglement and classical communication, which is not possible. Quantum entanglement is not possible with digital computer. Here, what you do is, first we need to create an entanglement. Absolutely, we use Kadamard gate. Alice and Bob, consider Alice, that is sender, and receiver hold the 1 qubit of an entanglement pair. Sender and receiver are entangled, but they do not share any information about the state of the qubit teleporter. Next step is we need to measure the Bell state. Actually, sender performs a Bell state measurement on her qubit, and the qubit she want to teleport. This measurement entangles sender's qubit with their qubit q and collapses the state in one of the possible 4 states in Bell state. Next step is we need to do classical communication. That is, sender sends the 2 classical bits of information to receiver over a classical channel. So next step is making the corrective operation by the receiver. Receiver, based on the sender's classical message, applies one of 4 possible quantum gates and gives entangled qubit to recreate a original state. After this operation, receiver qubit is in the XOR state as sender's qubit state, completing the teleportation process. So here the steps is we need to initialize with sender's qubit and Bob's qubit in an entangled state. Next, we need to use Bell state measurement by using controlled NOT gate followed by Kadamard gate. Next, we do classical communication. Finally, we apply condition operations, whether sender data and receiver data same. So this is the example for illustration for quantum teleportation. First, we need to generate entanglement, and we need to prepare a state. Then we need to join the measurement. Then we do condition transformation. Finally, we change to teleportation state. So the main purpose of using entanglement is the transfer of quantum information without physically moving the qubit. And also classical communication is still required to transmit the measurement outcome. Actually, quantum teleportation does not violate causality or enable the faster than highlight communication. Practical use cases of entanglement is, quantum teleportation is it can be used for quantum communication network and quantum key distribution cryptography. and quantum internet development. Next, I wish to discuss about hybrid classical quantum approaches. Here, I discuss about variational quantum circuit, which combines the power of quantum circuit for state preparation with classical optimization techniques to solve complex problems. Actually, variational quantum circuits involves parameterized quantum circuit, which is mainly used to approximate a solution. Will classical algorithm adjust the parameters to optimize the output, which consists of quantum circuit, classical optimization, and feedback loop. Quantum circuit is responsible for inputting the data and generate the quantum state, and the classical optimization mainly uses gradient descent optimization to iteratively adjust the parameters of the quantum circuit to minimize or maximize the objective. It is reduce the cost value, or if it is a maximization problem, means we can increase the cost. And also we have feedback loop, mainly evaluates the performance of the quantum circuit. For example, if it is a minimization problem, means we need to try to reduce the loss to zero. So every time in feedback loop, it checks whether the cost is coming close to zero or not. Zero for a minimization problem. If it reaches zero, means not reaching zero. If we closely, if the output or cost is close to zero, means we can stop. So we need to have a termination criteria for that. And we can use there is quantum circuit in quantum machine learning. Machine learning is responsible for identifying the useful patterns to reduce the running time while training the model. We can use quantum computing, and also for feature selection and reducing the loss, we are using the quantum machine learning. And also we use variational quantum coder in quantum chemistry simulation to solve the quantum eigensystem problem, such as finding the ground state energy of molecules. And also we can use it for finance. The VQC models can be applied in problems in finance, such as optimizing the asset allocation and optimizing risk management. Okay. And the main benefits of using VQC is we can achieve quantum superposition and entanglement. It can handle exponentially complex optimization problem. We can enable hybrid models with the help of VQC. We can apply classical optimization technique with quantum circuits, which acts as a practical approach for utilizing the quantum resources. We can also enhance scalability by using the VQC. Next, we can embed classical data into quantum state with the help of quantum machine learning circuits. Here, data is represented by using the quantum state. There is classical data such as image, text, or numerical data is encoded into quantum state through a process known as quantum data embedding. This is the thing asked by participants. And we can do data processing. There is basic encoding, amplitude encoding, angular encoding in data processing state. In basic encoding, basis encoding, each classical bit is mapped to the quantum bit. In amplitude encoding, data is embedded into the amplitude of the quantum state. In angular encoding, the data is represented in the rotation angle of the quantum gates. The main purpose of using encoding is it allows the exploitation of the quantum properties like superposition and entanglement to explore the complex data patterns in the high dimensional space. If data is of high dimensional, means classical computers may not be able to learn from the complex data. So if you wish to identify the suitable features, the best features to train the machine learning model to increase the efficiency, means we can use quantum encoding. And quantum classifier also is, uses a quantum circuit. The quantum classifiers are quantum circuits designed to classify quantum encoded data. They use quantum gates and measurements to process input data and output predictions. So these classifier makes use of quantum parallelism and interference to outperform classical classifiers for solving the problems. Next one is quantum support vector machines. It is an extension of support vector machine. Mainly support vector machines, we draw the hyperplane which covers all the all the vectors used for classification problem. The main advantage of using support vector machine is we can achieve higher accuracy despite you have a small amount of data. The quantum classifier encodes input data into quantum state and applies a quantum kernel. There is a transmission that computes the similarity between the data points in a high dimensional space, and then measures the state to determine the class label. So mainly used in classification problem. And next one is quantum neural network. Quantum neural network is the essence of neural network. In neural network, we find the association or relationship between the input vectors. Here, quantum circuits simulate neurons and weights. The main complexity in neural network is generation of optimal weights which best classifies the data. This task is done by the quantum circuits. And also we can achieve high-speed system. There is classifiers with alpha quantum computing, and we can learn from the complex feature spaces by using quantum circuit. And also we can achieve parallelism by using the quantum circuit process. The challenges of quantum circuit and quantum machine learning is noise and decoherence. Quantum computers are still susceptible to noise and errors, so which limits the scalability and the reliability of the quantum machine learning circuit. Next one is resource constraints. Large-scale quantum machine learning task cannot be solved by the single near-term devices. So we need computational power, more computational power to solve several machine learning problems. Next, another topic is role of circuits in simulating molecules. And this is completely different to quantum machine learning. We can use quantum circuit for making the simulations. Quantum circuits mainly useful for simulate complex quantum systems such as molecules, which are difficult or impossible to model with classical computers. The main goal of molecular simulation is electronic structure. Actually, quantum circuit mainly beneficial for calculating the molecular energies. We can simulate chemical reactions to get to know about how molecules interact and react with each other, and predict reaction outcomes and kinetics with alpha quantum circuits. So next one is variational quantum eigensolver, is mainly useful for simulation. Here, variational quantum eigensolver, we solve a quantum eigen problem, that is finding the ground state energy of the quantum system, such as molecule. I told about this. There is we make use of parameterized quantum circuit, classical optimization, and energy measurement for implementing variational quantum eigensolver. Application also I told mainly it is used in chemical molecule simulation, material science, and quantum chemistry. Advantage is speed up, and we can do accurate simulation. Challenge is it is susceptible to quantum noise, and we need more computational power. Now I wish to discuss about the challenges and future directions with respect to quantum circuit. We face challenges in qubits scaling. We have limited we have limited qubits. Current quantum processor have limited number of qubits. Also, we face issues like T occurrence. When number of qubit increases, means the decoherence also increases, which the environment affects coherence between the quantum bits. Also, gate fidelity. More qubits requires more gates, which leads to error accumulation. Error correction also is a daunting task if you use more qubits. And we face connectivity issues. There is a qubit coupling. There is a quantum circuit needs qubits to interact, but physical qubit arrangement often limit connectivity. And also layout of circuit, there is a logical qubit to physical qubit is challenging, which require many operations and introduce errors. And the solution for scalability of circuit, quantum circuit is we need to have facilities like quantum error corrections. Also, we need to have improvements, quality improvements and hardware improvements, which is initiated by IBM and Google. And also, we need to have a circuit optimization. We need to reduce circuit depth and gate complexity, which can improve scalability. And also, we can reduce. We can enhance the fidelity, circuit fidelity, by reducing the quantum noise. There is external disturbances can be reduced, and also we need to reduce the decoherence to achieve circuit fidelity. And to resolve error mitigations, to solve errors in the quantum circuits, we use quantum error correction methods, which protect quantum information by encoding it across multiple qubits. And also, we need to use dynamic decoupling, which involves applying the several control pulses to cancel out unwanted noise, which preserve the coherence for long periods. So, and also we face several limitations in terms of hardware. Already told about we face issues in limited qubits, and we face errors in qubit entanglement and all. So another issue is noise in quantum gates. Another issue. There are several kind of noise we have realized in hardware, quantum hardware, such as bit flip, phase flip, and so on. Now I used to discuss about my research paper, which is based on quantum computation. I think you are viewing the paper, research paper. My paper title is Discovery of Interesting Item Set for Web Service Composition using Hybrid Genetic Algorithm, which is published during March 2022. So here I have used the quantum computation in high-fidelity item set mining. Actually, high-fidelity item set mining is an extension of frequent item set mining. In frequent item set mining, we identify the high-frequent item set, that is a transaction which is frequently purchased by the customers. The main limitations of high-frequent item set is we may miss the item set which is infrequent, but it produces more profit. To resolve this problem, we have used the hybrid item set mining task. In hybrid item set mining task, we aim to identify the item set which is high, which produces more profit. So, for example, if you do a market basket analysis, supermarket owner only relies on the product which produces more profit. Okay, not on how frequently it purchased by the customer. Frequency does not matter, but utility plays a vital role to increase the sales, to increase the more profit. So we use hybrid item set mining here. Here, the problem with hybrid item set mining is it is a combinatorial problem. Okay, we need to, for example, if you have several transactions in the database means like this, consider you have a data set like this. So we have data set like this. This data contains the quantity, okay, purchase of item in terms of quantity. And also we have another table called utility table. So this is a simple toy example actually, which contains only seven that is 7 item set, 7 different item set and 5 transactions. Basically, number of products in the supermarket consists more than 10,000 actually. If you wish to identify the highly item set among the transaction means, we need to generate different combination of item set. There is combinatorial problem actually. The running time will be exponential if you use brute force approach to generate several combinations. So we are using several algorithms, tree-based approach and all. In tree-based approach and also we achieve running time may be reduced, but the running time will be exponential only. Okay, so we can also use a tree-based approach. So here number of candidates, number of items that generated is very high, even if you use a tree-based approach. So I have used an optimization algorithm here. Here I have making use of the power of genetic algorithm as well as optimization algorithm. I show the algorithm here. So here I used genetic algorithm as well as quantum computing algorithm. So here I represent chromosome in terms of qubit representation. See here, actual data set is represented in terms of, for example, item set is represented in terms of chromosome. So alpha, beta is a amplitude values. So this is the gene actually. So complete chromosomes represented in terms of here. So this is the example for quantum chromosome. Basically, if you use normal genetic algorithm means we don't represent amplitude value like this. We represent only in terms of quantity. Okay. So for every item, how many number of times it is purchased. Yeah, that is also done. And also, if you use binary chromosome means we can represent it as a 0 or 1. If you have one value in, if you having one value in a chromosome means it is a presence of an item. 0 means absence of an item. So since I have used quantum chromosome, I may represent chromosome like this, which consists several genes. Next, we need to encode the chromosome by using the vectors. Next, we need to use genetic operator. I use qubit rotations to generate a new state. Next, I apply crossover operation. And in this only, I just generate new offspring or new population by using the crossover operation. Next step is mutation operation. In mutation operation, I can generate new offspring by change the amplitude values in the chromosome. Next, we need to select the best chromosome for next population for doing the next iteration. Here, the fitness function is used to choose the best chromosome for the high item set mining task. The fitness computation is done by calculating the utility value. If you have an item set like this, the utility value computer like this here, consider this is a transaction I have. Utility value is computed for this transaction as this. The quantity is 1 more, so profit is 5. So we can identify the utility for A is 1 into 5. For C, value is quantity is 1 and utility also 1, so 1 into 1. For D, 1 into 2. Here we don't have any value for this, so just accumulate values you obtained. 5 into 1, 1 into 1, and 1 into 2. So totally we have 8. So in this way we can compute the profit value or utility value. So utility value is computed and you check whether it reaches the threshold. If it reaches threshold means we can consider that as a best population. So you can filter the chromosome by using the fitness evaluation. Okay. So after that you can generate highlight item set which reaches the threshold. So this is explained by using the algorithm. We have mentioned the algorithm. First we need to calculate the utility for every item, and you need to calculate the total utility of the transaction. Next we need to arrange the transaction descending order based on the utility. Because why I am arranging the data in descending order means we need to choose the population among several candidates. If for example I have 1,000 elements, 1,000 chromosomes, out of which I need to select only limited population means I can sort the data by using the descending order and identify the top 20. Next, create a population of fixed size, then construct that is construct the population, and there is population by computing the fitness values, then evaluating the fitness value, then consider as a highlight item set. Next, we need to apply qubit operations, qubit rotation, crossover, mutations to generate the new populations by using the iteration or while loop. Here we need to mention the termination criteria. Termination means you need to set the iteration size, and also if conversion happens means we can stop that. Conversion means new population is not generated by the qubit, I mean the crossover and mutation operation means we can stop that. So in this way we can generate the highlight item set which is published in neural processing data, that is Q2 journal. Experiment results are done with the help of several state-of-the-art data set which is obtained by UC repository. I have compared the running time, compared the performance of several algorithms by using the running time, I mean in terms of seconds, and by using memory space. Okay, and also I have compared by in terms of number of candidates generated actually. So and I have compared the algorithm in terms of fitness value. My proposed work generate highlight item set with more fitness value, so which is highlighted as blue. So this is the concept I have. I mean, I want to explain, which makes use of quantum computation actually. Okay. So there is similar to the quantum computing method. So number of candidate generated also is very high when compared to other approaches. Okay. Number of highlight items generated is very high when compared to other approaches. So I have performed a statistical test whether I have done correctly or not by using the Friedman test approach, which is asked by the reviewer. Okay. So I hope we understood the concept of how I can apply the quantum computing in machine learning. Hope you have understood this session. Now, I wish to tell about emerging trends, which I already told about emerging trends in quantum computing. Now, I present this screen. So, emerging trends, that is, in terms of emerging trends, we use topological qubits. It is one of the latest trend in quantum computing. We can encode the qubit information in the topological state of the matter. The main advantage of using topological qubit is higher stability and error resistance. Actually, Microsoft topological qubits are being developed to improve the error state and scalability. Another latest technology is fault tolerant circuit. We can do error correction and make use of redundant qubits to ensure errors in quantum computations that can be detected and corrected without losing information. Mainly, fault tolerant circuit is useful for essential essential for large scale quantum computers, where noise and degradations are significant challenges. Next, we can use it for application like pharmaceuticals, cryptography, and material science. We may assume that quantum processor in future quantum processor will scale to thousands of qubits, which will be very beneficial for us to reduce the running time of several algorithms, quantum algorithms, which is able to solve several problems efficiently. The key milestones will be based on developing the better algorithm, which unlock several applications, and also quantum networks, which is responsible for quantum communication, and quantum internet will transform data security. So these are the future of quantum computing. Thank you for the opportunity. If you have any queries, you can raise.
Thank you, sir.
Thank you. Do you have any queries? So I share the PPTs for these things. And also, I will answer some question which is relevant for.
Thank you, sir.
material
It was
science.
a very interesting session.
Thank you. Thank you, sir.
Thank you, sir.
Yes, thank you, sir.
Thank you, sir. Nice session, sir.
Thank you, sir. Thank you, sir. So one candidate asked quantum machine learning for material design. We can use machine learning for material science. That is, you can you can identify the behavior of the materials. Also, you can get to know about the quality of materials by using machine learning, and you can identify the defect, detect the defect, and forecast the failures in the materials used in the devices by using machine learning. You can first start with classical machine learning, and you can slowly move on to applying quantum machine learning in material design, material science, generally material science. We have also written some paper. There is application of machine learning in material science, which is published in one conference, Springer conference. I share the paperwork also to the participants to get to know about the applications of machine learning in material science. QML for security. Okay. Security means we can use QML for fraudulent activities, detecting the fraudulent activities, and also we can use it for intruder detection methods. We can also use QML for spam detection and all. Please note that we need to if you have large data means you can go for that is quantum machine learning. That is please ensure that your data consists of huge volume. It is either vertically as well as horizontally huge volume. So I have shared the DOI of my paper. Please make a note. Krishnamurthy sir, I just shared. Can make a note of it. Okay, sir. So you can, for security aspect, you can use it for intruder detection, malware detection, and all. Okay. First, try with classical machine learning and go for quantum machine learning if your data set is horizontally and vertically is very high. Thank you, Krishnamurthy sir. So if you have any query, you can contact by using my email ID, drkannimuthu@gmail.com. I have shared in chat box. Gopi sir, I have presented, sir. I stopped the session here. Any queries, participants? Thank you, Tenmuli.
Participant, if you have any queries, you can ask now. Kannimuthu sir?
Sir, tell me, sir.
Yeah, we can wait for a few more minutes or two.
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Yes, sir. I wait.
If anybody having queries, they can ask now.
Okay, sir.
Okay. Okay, so there is no question for your presentation.
Yes, sir.
Hello, participant. Do you have any queries? You can ask now. Otherwise, we can end the session.
So, a few persons asked a question through
chat box.
Through chat box, yes, sir.
Okay, okay. Yeah.
I answered, sir.
Okay, sir. Okay.
So, performance parameters of quantum algorithm. We can consider execution time and also noise. That is a performance parameter for a quantum algorithm. We can consider those two. So And also, if you use quantum algorithm for ML problem means we consider execution time. Then if it is a prediction problem means we can consider loss. It is square error, root mean square and all. If it is a classification problem means we can take accuracy, precision, recall and all. If it is a machine learning means something different. If it is a classical algorithm means mainly we use execution time only, execution time, and also noise. Noise also very, very important here. Thank you, Usali.
Sir?
Yes, sir.
Sir, thank you for your nice presentation.
Thank you, sir.
Thank you so much for your nice presentation for this session.
Thank you, sir. Thanks a lot, sir.
Thank you so much. Thank you, sir.
Okay, sir. I shall leave. Thank you, participants. Good night.
Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you so much, sir.
Thank you, sir. Thank you so much,
Thank
sir.
you, sir. Thank you. Thank you, sir.
Thank you, sir.